for which the system will work in saturation. Okay. So the option A is correct. I hope this question is clear to you. It's very easy problem, right? Let me take another question. The question given is simple BJT, base, ammeter and collector. In the collector the current is IC. In the base the current is definitely IB. Is it okay? And beta DC is nothing but the current gain, as you know, because beta DC is nothing but IC by IB. This is kind of current gain. Output is IC, input is IB, right? This is current gain, as you know. Is it okay? Now the question is, if the transistor in the figure is in saturation, this transistor shown in the figure is in saturation. They have given this saturation. This is working in saturation. Now you have four options. Option A is IC is always equal to, option 1 is IC should be equal to beta DC of IB. Option B is IC is always equal to beta DC of IB minus of. Option C is IC should be greater than beta DC of IB. Option D is given IC should be less than beta DC of IB. Now tell me which option will be correct. If you remember how to find the region of operation, in which we discussed 3 steps. The step first was to find out the IC saturation. Okay. In the first step you find IC saturation there. Okay. The first step was over. In the second step you find IC active. And IC active is nothing but beta IC. Beta IB. This is beta IB. Okay. So you found in the first case IC saturation, in the second case you found IC active. In the third case you compared. In the case first, if IC saturation is greater than IC active, means the transistor was working in active region. Why active region? Because IC saturation is greater than IC active. So it was working in active region. But if IC active was greater than IC saturation, this is faulty condition. This can't be possible with BJT. Why? Because IC saturation is the max current. No current can exceed to IC saturation. So in this condition, the condition was the BJT is working in saturation region. So condition was IC saturation should be less than IC active. So option D is clearly saying that IC is less than beta DC. This is active current, right? IC active. And this is saturation because they have given. And the condition is fulfilled. So option D should be correct for this. Is it clear to you? Let me take the next problem. And the problem is given, very simple problem. 10K of resistance or resistor connected in series with 10 volt battery. So where is the transistor? Here is the transistor. This is 1K connected like this, grounded, perfectly fine. Over here I have 2 volt and the circuit is closed. And the question is, let me erase it, it's not looking good. So the question is, for the BJT circuit shown, assume that the beta of the transistor is very large. You have to assume that beta is very large because beta is not given over here. And VB is 0.7. Over here the drop is given in the circuit question, and that is 0.7. The mode of operation of the BJT. The question is mode of operation. Find out mode of operation. This is your question. Okay. The same thing. 4 options are given for this. Cutoff. Option B, active. Option C, saturation. And option D, reverse active. Reverse active. Okay. This is very interesting problem. And this is GATE 2007 problem. 2 marks problem. Okay. So simply they are asking cutoff, active, saturation or reverse, and they are giving 2 marks. Why they are giving 2 marks to us with this simple question? Right. So we have to do something. See, they have given beta is large. What it means? If beta is large, it means IB is 0. Please remember this always. If beta is very large, so definitely your IB will be very low. So it's nearly about 0. Is it okay? The relation between beta and IB is, IC and IB is this. IC is always in terms of milliampere and something. Okay, fine. Beta is very large and IB is over here. Beta is very large. Very large means take it infinity. If this is infinity, IB will be 0. So it will be our assumption when beta is very large, you have to assume IB is 0. So in case if IB is 0, and what is relation between these 3 currents? Wait a minute. Between these 3 currents, IE is equal to IB plus IC. IB is 0. So IE is 0 plus IC. So it's IC. Now you are having IE equal to IC. So when beta is very large, IE will be definitely equal to IC. Okay. So let me write over here also. The condition is IE is equal to IC. Now, how we are going to calculate the system is working in active region or saturation region? First, the step 1 is calculate the saturation current. Saturation current. We have to take it 0. Okay. And if given in the circuit, so we have to take it 0.2. But not given, so I'll take it 0. Okay, but in practical case we take 2. Okay, so I can take 0.2, no problem at all. So this will be 0.2 divided by 10K plus 1K. This is IC saturation I'm going to calculate. Okay, so it will be 9.8 divided by 11K. 9.8 divided by 11 milli. So it will be 0.9 and something milliampere, nearly about the current is. Is it okay? IC saturation is done. Now how you calculate IC active? IC saturation is over. IC active will calculate by applying KVL into the input. This is the input. 2, no resistance, 0.7 drop, 0.7 drop. Okay. You have to complete the circuit. That's why we are switching, or we are going to the emitter region also. Here the current in emitter is IE. So drop is 1K IE and ground equal to 0. Is it okay? So this is the IE, and if beta is large, IE is equal to IC. So 2 minus 0.7. So 1.3 equal to 1K of IC, and this is IC active. Why? Because we get the value by applying KVL in the input. Whenever you are applying the KVL circuit or KVL law into the input, you will get IC active. Whenever you apply it at the output, you will get IC saturation. Is it okay? So your IC active is 1.3 milliampere. 1.3 milliampere. Now check the reason. Can you check it? Your IC active is greater than your IC saturation. Is it okay? So this is faulty condition. This is not possible. it means your VGT is working in saturation region. Saturation region. So your answer is option C. Is it okay to you? So if in 2 marks, very easy, we can get it in 30 seconds to 1 minute only. So friends, I would like to tell you one thing. Please follow the steps whatever I told you. First, you have to find out IC saturation. Second, you have to find IC active. And in the third case, you have to compare. And in the comparison, if IC active is greater than IC saturation, so your system will work in saturation always. If I saturation is greater than IC active, then your system will work in active region. Okay. I'll take another problem, and this is GATE 2014. GATE 2014, and the problem is 2 marks problem. Again, easy problem, right? So the problem given is, let me draw the circuit first. Plus 10 volt, perfectly fine, connected with RC, grounded, 50K and 5 volt. Is it okay? Wait. So this is the question given, and the question in the circuit shown in the figure, the silicon BJT has beta value is given 50. Assume VBE is 0.7, VBE as always. VCE saturation is also given, and that is 0.2. Which one of the following statement is correct? The question is, which one of the following statement is correct? The first statement, option A, is RC equal to 1K, and if this, then transistor will work in saturation. This is option A given. Option B, for RC equal to 3K, the same saturation. Option C, if RC is 20K, then there will be cutoff region. Option D is, if RC is 20K, BJT operates in linear region. Linear means active region. Okay. So these are the condition given, and we have to check one by one. Okay. This is the circuit given over here, and the values beta, VB, VC is given. The question is, the circuit will be in saturation if RC equal to 1. It will be in saturation when RC equal to 3K. It will be in cutoff when RC equal to 20K. It will be in linear or active region when RC equal to 20K. So I'll start the circuit by assuming that circuit is in active region, suppose. Let me erase this portion now. Okay, let it be like this, no problem. So suppose I assume the circuit is in active region. Suppose I assume this. If this is an active region, the circuit is in active region, I have to find the values by applying the VBE and beta in the input. See, this is 0.7 given over here. I applied over here. Okay. So can we find out IB? It will be IB active. I can give the name IB active. So this IB active will be 5 minus 0.7. This is the 0.7 divided by 50K. So this is 4.3 divided by 50K. Is it okay? So it will be nearly about 86 micro ampere. Okay. If you calculated IB active, can you calculate IC active? IC active. You can calculate IC active, yes. IC active is beta IB. What is beta given over here? 50. 50 is given over here. And IB active is nothing but 40 divided by 50K. So this is 43 milliampere. So you calculated IC active, means current here is 43 milliampere. Okay. Now, the interesting thing over that we have to calculate RC. They are not asking for IC and all this. Let me erase this part, then I'll come to the point. This part is done. So the interesting thing is we have to calculate we have to calculate RC over here, right? So suppose RC is something, we'll assume by option only. Okay, let me take pen first. See over here, which diode is given over here? Collector to base diode is working over here, right? Okay, let me see for saturation. If I'll talk about saturation, for saturation I have two junctions, right? Emitter base junctions and collector base junction. For saturation, the emitter base junction should be forward bias, collector base junction should be forward bias. Is it okay? But if you are in active state, your EB should be in forward bias, your CB should be, collector base should be in reverse bias. So we'll check the condition. According to this, we'll find the RCC. Now, we are having two options to select the RC. We may select 1K, we may select 3K or 20K. Okay. Suppose I'm choosing 1K. RC is 1K suppose. RC is 1K. In the 1K, the current is 4.3 milliampere. So there will be drop across this, and that is 4.3 volt. If 4.3 volt is the drop across here, so at this point 10 minus 4.3, this is 5.7. 5.7. This is the 5.7. Let me draw this unnecessary thing so it will be clear to you. This 50K is gayab. Okay, everything is gayab from the circuit. So let me draw it again. Okay, like this. This point at 5.7. Here is the diode, like this. Here is the diode. Okay. Remember in first class I mentioned these two diodes. If this is collector, this is emitter, and if this is base, and you have chosen NPN and PN. So this is two diode circuitry like this, like this. Okay, this is the anode part of the diode because base region is P type. So here also I'm using the same symbol in same direction. Now my condition is, this is collector, this is base. If this collector base junction is in forward bias, and I have diode over here also. Okay. See, this is base and this is emitter. Okay. So check the condition of this. This is forward bias or reverse bias. Here it's a 5 volt and something. Definitely after some drop it will be positive, but this is grounded. So this will be in forward bias. So you can see the emitter base junction is in the forward bias region. So we are getting it into forward bias also, we are getting into saturation. In the both case this condition is okay. This condition is okay. But we have to check the reverse bias condition or the collector base condition. Come to this. If this is 5.7, if this is 5.7, and obviously this will be in reverse bias condition. Is it okay? This will be definitely in reverse bias condition because 5.7 is greater than 5 over here. So the reverse bias condition is coming into active region. So the condition of this entire circuit is the emitter base junction is forward bias and collector base junction is reverse bias for RC equal to 1. RC equal to 1K. So do we have option that for RC equal to 1K the circuit is inactive? No, we don't have. Here we have 20K and it's active. Is it okay? So we don't have that. Now we have to move this to 3K. Now we move to 3K. Current is 43 milliampere. Resistance is 3K. So 43 into 3. So it will be, wait a minute. I'm sorry, this is 4.3 milli, okay. So 4.3 into 3, it will be 9 and 12. So the voltage over here will be minus 2.9. Now at this stage, this diode will be in forward bias. So once this diode will be in forward bias and input diode is also in forward bias. So this is the condition for saturation. So for RC equal to 3K, the circuit in saturation. Is this condition given over here? RC equal to 1K said no. RC equal to 3K, it's saturation. Yes, it's given over here. So this should be the answer. Is it okay? So I hope this part of the question is very clear to you. If it is not clear, again I'm telling you, again I'm showing that figure to you. This is emitter part, this is collector part, and this is base part. This is collector. Base to collector you have one diode, and base to emitter you have one diode. If this diode both are in forward bias, your circuit will be in saturation. If this is forward bias, this is reverse bias, your circuit will be inactive. If this is in reverse bias and this is in reverse bias, both are in cutoff, circuit in cutoff. If this is reverse bias, this is in a forward bias, your circuit will be in reverse active. So for the previous question, what we have we got there that this was forward bias and this was forward bias. We get this forward bias for RC equal to 3K. That's why we have chosen the second option. Is it okay? So I hope this is clear to you. Now we'll come to the next topic into the unit, and that is the stability factor. So last time we were discussing about how to choose our Q point, where we have to choose. And I told you that our Q point should be in linear region. So the output will be the complete replica of the input, or I can say the amplification will be perfectly done over here if you are choosing your Q point in this region or the linear region. Okay, so it's very necessary, or the need of time to choose Q point in such a way that you are not getting any distortion. See, we are having 3 cases given over here, and for 3 different cases I'm getting different output. If instead of this you are choosing your Q point over here near to cutoff region, okay, let me erase some part. Wait a minute. For this circuit we are choosing our Q point near to cutoff region. If cutoff region is your Q point, see, this much is your Q point. When you will apply AC will fluctuate near to Q point. Okay, so some part of AC will go into the cutoff region if you are choosing this Q point at cutoff. So at the output, what will happen? This part of the region or your input will cut off, clipped. See, this much part, for this part it's okay, no problem at all. But for this much part it will be cut off. Why? Because when you are considering your Q point near to cutoff region, some part of the input is going into the cutoff. The system or the output is like C. You can understand by this. This is your Q point, and your Q point is coming to the in cutoff region like this. Here you are applying the input like this. Suppose let's take it. Here is the input. This is the output MAV, right? So output MAV will be from this, not from this point. Okay, because this is the cutoff point for the output. So in this case, for this positive half cycle, it will come over here. But for negative half cycle, this much of the portion will cut down. Okay, let me show it in the fresh page. See, what I'm saying is, you have chosen your Q point in cutoff, near to cutoff region. This is the cutoff of transistors. Okay. And here you choose your Q point. And I told you that if you are applying AC to the BJT, the AC will fluctuate, or the output will fluctuate near to Q. Right? And this is your input you are applying. Here you applied your input. This is input part. Positive half cycle, negative half cycle. Okay. What is the output mapping? Output mapping is like this. So this is your cutoff region for output. So output mapping will be up to here only, not up to here. This is your output mapping. Now, how the waveform at output will be? For this entire positive half, it will be mapped at output, no problem at all. What about this? If you want to map this negative also, it will come up to this line. But after this line, your transistor is in cutoff. At the output stage, you are not getting this portion. This is the complete cutoff region for your transistor. Is it okay? So you are getting distorted waveform. You are applying input, perfectly fine waveform, but at the output you are getting distorted waveform. So this is the drawback. We can't choose the Q point near to cutoff. Okay, let's come to the point there. Wait a minute. So if you are choosing your Q point near to cutoff, you are getting distorted output. Your output is distorted. We can't choose it. What if you are getting your Q point near to saturation? Near to saturation, if you'll get, again you will clipped your input, but this time positive half will be clipped. In the cutoff region, we clipped our negative part. In the saturation region, we'll get clipped our positive part, or positive half. So we can't choose Q point near to saturation. We can't choose Q point near to cutoff. So where we have to choose? It is best to choose Q point at the middle of the load line. And you know about the load line. For the output circuit, if output characteristics I'll talk about, that load line will be drawn in between VCE and IC. Okay. At this point, the VC will be max. At this point, the IC will be max. And the Q point will be the mid part of this line. When this is the mid part, so in this case, there will be no distortion. You will get complete output. See, over here, this entire thing is mapped over here without any distortion. So for the better amplification, your Q point should be at the middle of the load line. If the operating point is selected in the middle of the active region, and it should be in active region. This is the active region, right? This portion is active region or not? This is the saturation region, this is the cutoff region, and this is active region. Okay. If the operating point is selected in the middle of active region, then there is a no clipping, and the output follows input faithfully as shown in the figure. Is it okay? You can see over here. If input is large, then clipping at both sides will be take place. If input is very large, if your input is very large kind of, so you'll get clipped at upper stage in the positive half also, in the lower stage in the cutoff region also. Okay. So the first circuit for biasing the transistor is CE configuration is fixed bias. We have seen the fixed bias. These were the details we were discussing over fixed biasing. Is it okay? What is next? Stability factor. This is the very important point as per the, the output characteristic is concerned, because we have to choose the Q point perfectly. So there we need to discuss about the stability factor. The operating point can be made stable by keeping IC and VCE constant. Why? Because your Q point is drawn on the load line, and load line is drawn in between VCE and IC. So this load line is affected by IC and VCE or not. So if you'll choose VCE and IC constant, we can control this Q point position, or we can locate the Q position. The position of Q is in our hand. Okay. So the operating point can be made stable by keeping IC and VCE constant. There are two techniques to make Q point stable. The first one is stabilization techniques, and second one is compensation technique. In the first the stabilization technique, resistor biasing circuit are used which allow IB to vary so as to keep IC relatively constant with variation in this is beta, ICO and VBE. Okay, what is the point? If you want to keep your Q point at particular position, or I can say you want to keep it stable, what you have to do is you have to keep constant IC and VCE. This is your task. How you can keep IC constant? There is a variation in IB. There is variation in IB. And IC is also function of beta. It is dependent on beta. It is dependent on load variation also. It is dependent on VBE also. See. So, we have to keep constant all these parameters, then only we can keep constant to IC. And once you keep constant to IC, your Q point is stable. If your Q point is stable, you are doing amplification very perfectly, right? So to keep this beta constant, this IB at certain level, this RC at certain point, you need different biasings. Like fixed biasing, potential divider biasing, collector feedback, emitter, resistor, like this, so many we'll discuss about this. So I think this point is very clear to you why we are doing biasing. Biasing we are doing to control these parameters mainly. Because once you control these parameters, you can control IC. Once you control IC, your Q point is stable. Your Q point is stable, your amplification is perfect, right? So to compare different biasing circuit, stability factor ACE is defined as the rate of change of collector current with respect to ICO. The mathematical way to represent this ACE, the stability factor given by ACE, and ACE is rate change of, the ACE is defined the rate change of collector current with respect to ICO given by del IC divided by del ICO. With respect to ICO, we are changing IC. This is the minimum leakage current over which we are looking for IC. This is your stability factor. Is it okay? So to compare different biasing circuits, stability factor ACE is defined as the rate of change of collector current with respect to ICO, keeping beta DC and VCE constant. Our assumption is beta DC and VCE is constant. So by doing this, 2 points are constant, right? Beta DC and VCE. Beta DC and VCE. We need these 2 points constant to make IC constant, right? So the stability factor is again given by del IC by del ICO. Okay. Now, if ACE is large, stability factor is large, then circuit is thermally unstable. It will be thermally unstable. So ACE can't be less than unity, and ACE can't be less than unity. ACE is always greater than unity. Okay. Because IC will be, the variation in IC will be, greater than variation in ICO. Okay. So the other stability factor are del IC by del beta C. Means here we are checking the variation in IC with respect to beta, or del IC by del VBE. So why we choose ICO? This ICO is the combination of this thing, because ICO is depending on temperature, right? This is totally temperature current. An effect of stability of IC is affected due to this temperature only. Beta is also the function of temperature. So that's why I'm choosing ICO over here. So the bias circuit VB, the bias circuit which provides stability with ICO, also shows stability even if beta and VPA changes. That's why we are choosing ICO. If you are considering ICO, by default you considered beta and VBE. That's why for the stability factor we are looking with respect to ICO. The point is clear now. Okay, let me erase some part. So IC is beta DCIB. As I told you earlier, original IC is given by beta IB plus beta plus 1 of ICO. Okay, we only choose this one part, right? Why? Because ICO is very small. This is in nanoampere current. So we neglected this, right? So suppose in original way we are taking this equation given over here. This all B is nothing but beta. Now we'll differentiate this equation IC with respect to ICO to get stability factor. When you will differentiate it, you will get the stability factor 1 plus beta. I'll write over here 1 plus beta 1 minus beta del IB by del IC. Is it okay? So see, here the variation of IB with respect to C given over here. So in fixed bias circuit, IB and IC are independent. In the fixed bias, IC and IB both are independent. Therefore, del IB by del IC will be 0. This part will become 0. So your stability factor will be 1 plus beta. Is it okay? Stability factor is 1 plus beta. If beta DC is 100, so it will be 101 definitely, which means IC is increased 101 times as fast as ICO. Is it okay? Now, such a large change definitely operate the transistor is in saturation region. This is the, see, such a large change definitely operate the transistor in. So this change is very large. So I can say the transistor is working the saturation in that case when the change is very large. Okay. So this is about the stability factor. So in the biasing only, now the next biasing is emitter feedback biasing. So till now what we have done is, we have seen why we are doing biasing. And what is the definition of biasing? Is it okay? Biasing is to done to shift the input. Is it okay? To keep constant IC, or the IC should not depend on beta, RCE and VB like. Okay. By doing this and keeping Q point in operating region. So we can call it the Q point is nothing but the operating point also. So this is the fundamental, the work of biasing, function of biasing. So in that we have seen the fixed bias case. The first case we have seen is the fixed bias case. Now second one is emitter feedback bias. Emitter feedback bias. See, in this emitter we have chosen in the first case, fixed bias case, the emitter was directly connected to the ground, but in this case, emitter is connected with RE. So in other words, I can say this biasing is emitter resistor biasing. Emitter resistor biasing. Okay. So this is the circuit. So for all biasing, we have to remember the circuit diagram only. How we are going to connect it. If once we are able to know the circuit, we can apply the circuit theory and we can calculate anything, whatever they are asking. Mainly they will ask for gain, input, output, V in, V output. Okay, this type of question we are getting in GATE exam. They will give one question and we have to apply. They are not saying that this is fixed bias, this is potential divider, or this is emitter feedback. You have to apply the formulas and you have to get the answers. Okay, when I'll come to these problems, this part of the problems, it will be very clear to you that there is no use to remember this thing only. This emitter bias or fixed bias or whatever. You don't have to remember this. Directly we have to apply and get the answers. Okay. But this is the part of the syllabus, so you have to cover it. In the figure, you can see, shows the emitter feedback bias circuit. In the circuit, the voltage across resistor RE, the voltage over here is used to offset the change in beta DC. What is our concern? Why we are doing biasing? To keep this beta constant. So if we'll keep this RC into the circuit, it will do something to maintain beta constant or independent of temperature. So what will be there, we'll see in mathematical way. So again I'm telling you, RC is used to offset the changes in beta DC. If beta DC increases, the collector current increases. If beta increases, collector current increases. This increases the emitter voltage, which decreases the voltage across the base resistor and reduce base current. Okay, when IC will increase, it will increase emitter. This increases the emitter voltage also, which decreases the voltage across the base resistor. In this resistor, the base will drop. The current will drop, right? This increase the emitter voltage, decreases the voltage across base resistor and reduce the base current. So the reduced base current result in less collector current. Why? Because collector current is beta IB. If IB will reduce, what you are going to do? You connected RE. Because of this RE, when beta will increase, IC will increase, the emitter current voltage will increase. When emitter voltage will increase, the V means voltage across this RB will decrease, so current will decrease. Okay. Up to now we have completed. Now the reduced base current result in less collector current. This part is okay, which partially offsets the original increase in beta DC. So this thing will partially, offset the original increase in beta DC. Because of beta DC, this part is decreased. This is decreased, so ultimately IC is decreased or compensated. See, when beta will increase, IC will increase. But here, if IC, there is a change in beta, there will be change in base current will decrease. If base current will decrease, so IC should be decreased. But in this case IC increase, in this case IC decrease, so it will be compensated by this. Okay, so there will be no effect on IC because of beta changes. So the feedback term is used because output current IC produces a change in input current IB. So because of this we are using the feedback. Okay, now RE is common in input and output circuit. In input and output circuit, the RE is common. So this is the emitter biasing, right? Now for this circuit also we'll apply KVL in the input, in the output also, and we'll be having two equations. Let's check the equations. So this is I applied at input stage and I equal to IC plus IB. Finally, what is my intention? My intention is to check S. I have to calculate the stability factor, correct? In this case, S is less compared to fixed bias. In this case, stability factor is less than to the fixed bias. Thus, the stability of Q point is better further. Okay? Means the variation in stability point is less compared to fixed. So further, if IE and minus IC, IE is equal to IC equal to this is given. So what is my intention is, if IC is to be made insensitive to beta DC, then now this is the condition. See, if you want to make IC to be independent of beta DC, what you need to do is your RE should be greater than RB by beta DC. This RE is in your hand or not. So how to choose this RE? This RE should be greater than RB divided by beta DC. RB is given in the circuit. You can see in the circuit RB is given over here. So if you want to make, first I'll tell you one thing. If you are choosing emitter bias circuiting or emitter biased feedback, emitter resistor feedback bias, you can say you are choosing this. What you need to do is, what is your intention? Why you are choosing is, your intention is to make IC not dependent on beta or change in beta. Right? This is your goal. So if you want to do so, what you need to do is, you need to choose RE very large to RB and divide by beta DC. Okay. Whatever RB value is there, divide by beta DC, whatever value you are getting, your RE should be greater than that value. Then this will be perfectly amplifier. This will work as a perfectly amplifier, or no distortion you will get at the output. Are you getting me? So RE can't be made large. So this is another restriction. RE can't be made large enough to swamp out the effect of BTDC without saturation the transistor. So it has its own limitation. So we'll come to the next one, and that is the collector feedback biasing. In this, the collector is feedbacked like this. Is it okay? In this case, the base resistor is returned back to collector. This base resistor is returned back to the collector as shown in the figure. If temperature increases, beta DC increases definitely. This produces more collector current. Collector current will increase because we have seen this. If temperature increase, beta increase. If beta increase, collector current increase. Right. So up to here we completed. Now as IC increases, collector emitter voltage decreases. Now collector emitter volt will decrease or not? VCE will decrease. Definitely it will decrease because the maximum drop will go to the load part. So VCE will be very less. So VCE is going to decrease. So it means less voltage across RB. Yeah, perfectly fine. And cause a decrease in base current. This decrease in IC and compensating the effect of beta DC. So in this case also we are compensating the effect of beta DC. What is going on? Temperature increasing, beta increasing, IC increasing, VCE decreasing. If VCE is decreasing, the base voltage is decreasing because of IB decreasing. If IB is decreasing, collector current IC will also decrease. So in this case, this will be compensated by this. Increase and decrease. Finally, compensated at the constant level. Okay. So RB cause a decrease in base current, this decrease IC and compensating the effect of beta DC. So I hope this point is clear to you. Okay. So here also what we are going to do, we are choosing the biasing circuit in such a way that your IC should be constant. Because for the better stability or amplification, we need to keep constant our IC, right? Come to the next. Here is the calculation given for this circuit also. You applied at output stage, you are getting something, and finally you are getting del IB by del IC, and this is the formula for S. And finally what you are getting is, it is better as compared to fixed bias circuit. Further, IC is given by this. Circuit is still sensitive to changes in beta DC. See, beta DC part is coming. This IC, what we need to keep constant IC. IC is VCC, VB, RC. So here also the beta part is coming over here. When beta increase, this will decrease. When this will decrease, this entire part, the IC will increase, right? So the advantage is only two resistors are used. The advantage of collector feedback is the resistance are reduced. Okay, so power consumption will be less. Power rating will be good for collector feedback. Is it okay? Now we are having voltage divider biasing also. This one is very important. So how to do this? See, in the voltage divider biasing, there will be two resistances connected in this way, R1 and R2 over here from base. This is VCC, this is collector current or collector resistor C, E and B. In the voltage divider, we are using RE also. If we'll consider this much part only, it's collector feedback. If we'll consider this one also or resolve it, it will become fixed bias. This is the mixing kind of thing, right? So I need to come with equivalent model of this. Equivalent model means when you will do the DC analysis of this, R1 and R2 will be in parallel. So this R1 and R2 will be parallel. So I'll become with the resultant. So the resultant RB will be R1 parallel with R2. and the formula is R1 R2 divided by R1 plus R2. Is it okay? This is your RB, and you have to calculate voltage across this also. That will be your resultant. What you are doing, you are finding the resultant of this or Thevenin equivalent of this. Up to here I can say. Okay, so now this voltage will be R2 into VCC divided by R1 plus R2. This will be the voltage over here. Now this your outer circuit is same as the previous one. See, same as this one only. Everything is same, no changes over here, but your input part is modified. What we did, we take the equivalent model of this. Okay, so what will happen with this? Here also, this is the Thevenin you applied at the input stage, and you are getting this. RB is the effective resistance seen back from the base terminal. This RB is the effective resistance. Okay, so you applied input KVL equation, so you are getting this. From this equation, you have to check del IB by del IC, because in our fundamental formula is we have need of this IB by IC. So this del IB by del IC is nothing but this. You have put in the S. So what you are getting is, again you have to make it independent of beta DC. So your RB by RC, where is it? RB by RC. Or RB by RE you can take it. What will happen, you know? When RB by RC is going to 0, then stability factor is going to 1. Is it okay? But when RB by RC is going to infinity, the stability factor is going to 1 plus beta. In this case, right? So I'm telling you again, this biasing circuits are not very much important. You have to see that this is the biasing, because in the problem portion we'll apply the circuit theorems and the circuit ideas, and we'll get the answer, right? So in this case, the smaller the value of RB, the better is the stabilization, but S can't be reduced by unity. This is the resultant effective, right? Hence IC is always increases more than ICO. If RB is reduced, the effective resistance of base, then current drawn from the supply increases. Perfectly fine. Also, if RE is increased, then to operate at the same Q point, the magnitude of VCC must be increased. In both the cases, the power loss increased and reduced H. Right? Oh, let me tell you. In order to avoid the loss of AC signal because of the feedback caused by RE, this resistance is often bypassed by a large capacitance in the range of this, so that its reactance at the frequency under consideration is fairly small. I'll come to the point. So in the next class we'll see the emitter biasing, and we'll bind up this biasing part. We'll switch to the small signal analysis, that is the AC analysis and DC analysis we'll do. So friends, we'll meet in the next class. Till then, take care and bye.